Hey guys, welcome back to Electricity Whiz. Today I'm going to be teaching you about
Delta and Wye Transformations.
My name is Sheehan and I'm a graduate student in electrical engineering, and I want to teach you everything I know about electricity in the best and most enjoyable way I know how. Enjoyable? Well, at least I'm going to try. So stay tuned for this episode of
Delta and Wye Transformations. If you haven't seen my previous video about Ohm's Law and you're not sure how it works, please visit that video first before you watch this video. Just to recap from the last video, components such as resistors are said to be in series when they are in a row with only one path for current to flow. They can be combined into one resistor by adding them together. On the other hand, components are said to be in parallel when each side of each component is directly connected to a node with each side of the other component. Parallel resistors can be combined into one resistor using the following equation. Sometimes we run into a situation where we're trying to combine resistors in a network, but we find that we have a network of resistors that we just can't combine because they're not in series or parallel. Look at this circuit. There are no two resistors in series because current has more than one path to flow between any of them, and no two resistors in the circuit have both sides directly touching, so neither are any of them parallel.
Well, we're going to put some tools in our toolbox so we can turn this circuit into this circuit, and this circuit we know how to solve.
Delta-Wye transformations allow us to transform resistors in a delta configuration like this into a Y configuration like this, and vice versa. Once we do these transformations, usually we can then finish solving the circuit using normal series parallel techniques. The most logical way to approach this transformation is to imagine the Y resistor network inside the delta resistor network, like this. You will notice that both have three nodes that share exactly the same connection points to a larger circuit. Once you have done this, it becomes just a task of remembering how to get each configuration from the other. If we start out with a delta configuration, we need to remember that each resistor in the Y circuit is just the multiplication of the two surrounding delta resistors divided by the sum of all the delta resistors. So this means that in this case, RA equals R1 times R2 divided by R1 plus R2 plus R3. RB equals R1 times R3 divided by R1 plus R2 plus R3. RC equals R2 times R3 divided by R1 plus R2 plus R3. Now we just match our connection points and replace the delta configuration with the Y, and voila, an equivalent resistor network. But what if we start off with a Y configuration? Well, it's basically the same process, only in reverse. In this case, each delta resistor will have a value of the sum of the products of the three Y resistors divided by the opposite Y resistor. So R1 equals RA times RB plus RB times RC plus RA times RC, the sum of the products, divided by RC. R2 equals the same numerator divided by its opposite resistor RB. R3 equals the same numerator divided by its opposite resistor RA. Notice here that all the numerators are the same, and only the opposite resistor goes in the denominator. While doing these transformations from Y to delta or from delta to Y, it's always a good idea to draw them out overlapping just like this. It eliminates a lot of confusion with the connections and aids the memory with the equations. In engineering, it is always a good practice to, when in doubt, draw it out. So let's go back and look at our original circuit now. We can't perform any series or parallel combinations, but we can identify a 3-point Y connection here. Let's change it to a delta.
Keeping our three connection points the same, we can use the previously discussed tactics to determine the value of the delta resistors and then replacing it into the 3 points. Don't worry if this looks like a very different delta circuit than you saw before. You need to get used to understanding the idea of voltage references. The three connections of the delta Y are voltage reference connections. As long as the three voltage reference points of the final configuration match the three original voltage reference points, then you have an equivalent circuit. The important thing with this method is to be able to recognize when you can make your life easier and do these transformations. Usually when you can't reduce a resistance network anymore using series parallel techniques, you should see if you can use this method instead to break down your circuit. Another very common use of this transformation is in a bridge resistor network like this one. This can be solved in a very complicated way by using KVLs and KCLs to get currents and voltages. But it's much easier to recognize that there are delta connections and to transform one of the delta connections into a Y connection. This just makes life so much easier, and engineers love making hard things easy.
Alright guys, that about wraps it up for today. Thanks for stopping by my channel, Electricity Whiz. If you liked the video, please give me the thumbs up. It helps a lot. If you want more information about future content, subscribe and hit the notification bell. Don't forget to hit the notification bell. And I'd love for your feedback in the comments section so that I can make these videos better and I can give you better quality content in the future. Peace.